we just want to list out what we know about this polynomial. So it has a higher degree of a power of 8, and we want to just find out what information we can get without actually solving it. Well, the first thing I noticed, if you go back up to the very first page, I think it's at the bottom of that first page, I give you a little note, or maybe it's the top of the next page, but there's something in there that talks about how if you have a common power of x, you always have to consider that first. So that's talking about x to the, it's talking about your zero root. So if I go in here, I know that everything in here I can factor out an x cubed, because that'll leave me with x to the 5th minus x cubed minus 5x squared and plus 1. So what I know for a fact is that x equals 0, because if I went ahead and set x cubed equal to 0 and the other part equal to 0, x equals 0 is a triple root. Okay, that's part of my answer, because what we need to do is determine what information can be found about the roots. Well, I know that x equals 0 is a triple root. So now when I go through and do these sign changes, really all I'm looking at is this back part, and I'm looking for 5 more roots. Okay, so let's look for the positive roots. Remember, the positives, all we do is take the function as is, and I'm going to just focus on this middle one right here, the factored part. So I have x to the 5th minus x cubed minus 5x squared plus 1. And I want to count the sign changes. So from positive to negative, there's 1. Negative, negative, nope. Negative to positive, there's another 1. So I have 2 sign changes, or 0, because we always subtract 2. For the potential negatives, then I'm going to go and change the sign from the odd powers. So that's going to be negative x to the 5th, a positive x cubed. The square is not going to change, and then of course the 1's not going to change. So if I count there, negative to positive, there's 1. Positive to negative, there's 1. Negative to positive, there's 1. So it looks like we get 3 or 1. Okay, so when we list this out in a chart, this time we have a column for positives, a column for negatives, a column for imaginaries, and we have to incorporate a column for 0, because we know that 0 is a root. And 0 is neither positive, negative, or imaginary. It's just, since it's a triple root, no matter what, we can go down and put 3's all the single time. Okay, so here's a combination. So for positives, so I can either go 2 positives and 3 negatives, 2 positives and 1 negative, 0 positive and 3, and 0 and 1. Just kind of matching those up. And I know that each row has to sum to a grand total of 8. So 2 plus 3 is already 8, so no imaginaries there. 2 plus 1 is 3, and 3 is 6, so 2. 0 and 3 is 6, so 2. 3 and 1 and 0 is 4, so 4. And that right there is a great description on the information that we can find about the potential roots. So if I go in, there's a 50-50 chance that you could have either 2 positives or 0 positive roots. Kind of something to look at. Let's try example 7. Here in example 7, we're basically just trying to find more information again about our roots. It gives us a polynomial that has a degree of 20. Okay, so the overall degree for this polynomial is 20. So I should be getting 20 roots altogether total. Some of these are going to repeat, obviously, because it tells us for a fact that x equals 2 plus 5i has a multiplicity of 4. And because we really know all about conjugates and how imaginary numbers come with conjugates, we also know that 2 minus 5i then also has to have a multiplicity of 4. Okay, if I go back up into the original problem, just ignore the whole a and b part right here. It looks like we have a power of, we can almost factor out an x to the 5th. So x to the 5, if I pull that off, you'll get x to the 15th plus x to the 9th plus 1 equals 0. So in other words, x to the 5, or if you want to consider it, let's write it out more like this, is that x equals 0 has a multiplicity of 5. Okay, so what have we just found so far? Out of a total degree of 20, I know that 4 are going to be this imaginary number, 4 are going to be this imaginary number, and 5 are going to be x equals 0. Okay. The question says, though, what is the maximum number of different real roots? So we really don't care about these two imaginary other than the fact of together 8, so that's going to knock our degree down to 12. So if we take out the imaginary, then there's 12 potential non-imaginary roots. However, of those 12, we know that 5 of them are the same root. 5 of them are x equals 0, x equals 0, x equals 0, and the key is it wants different real roots. Okay, so if we go up there, okay, so of these 12 potential non-imaginary roots, we know 5 of the 12 are x equals 0. So if we can kind of combine these two ideas together, then what that leaves us is 7 potential other roots. Okay, now the question though, this is where it gets a little tricky. It says, what's the maximum number of different real roots? So if we throw out the imaginaries, that's going to take us down to 12. But of the 12, a group of 5 of them were x equals 0. So the answer then is for the potential different real roots. So for the different ones, then what we have to do is consider the 7 other potential plus the one group of zeros, that mega one group of zeros that we got in there, and there's a total number of 8. So that's the answer to the problem, because what you have to do is consider the other 7 potentials that we can get, but you have to include the one group of zeros. So all 5 of those, consider that as one big group, because they're real. They're not imaginary, they're real, but they all just lump them together as considering one group of, or one real number. Okay, and that gives you a grand total of 8. Okay, let's go on to the last example for this section. Okay, and to wrap this up, here in example 8, we're giving a polynomial 2x cubed minus 5x plus 2, and we know that we have roots that's falling between -3 and 3, and we're going to use the intermediate value theorem to locate the actual real roots of it. Okay, we haven't done much with the intermediate value theorem, but it's not that hard at all. That's why I was like, I'm just going to wait until an example to show you, and we can get it all done in pretty much one example. What you want to do is just give yourself a sign chart, and it says that we know that each of the roots needs to happen on consecutive integers, so consecutive meaning back to back. And we're going to go from 1 to 3 because it tells us that in general we're going to go from -3 to +3. Okay? And all you want to do is plug in these numbers and get the magnitude out, or get the, not the magnitude, but the sign out. So in other words, if I plug in 0, what comes out? I don't really care if it's a 5 or a -10. I just want to know, is it positive or it's negative? So if I plug in 0, then obviously 2 times 0 cubed minus 5 times 0 plus 2, those go away and I get a +2. So it's positive right there. Okay. If I plug in 1, 2 times 1 cubed, so 2 minus 5 plus 2. So 2 plus 2 is 4, minus 5 is negative. That's all I care about. If I plug in +2, so 2 times 2 cubed minus 5 times 2 plus 2 is 2 times 8, which is 16 minus 10 plus 2. That's definitely positive. Okay, so what I want you to do is finish out the rest of the numbers, hit pause, finish these out, and let's compare what we get, okay? Okay, so hopefully you've gotten about the same sign chart that I got and how to interpret it. So this is the intermediate value theorem. When you're representing the negatives and positives, what it's telling you is when you're below and above the x-axis. So like, for example, when you're at x equals -3, your graph is going to definitely be below the x-axis. Same thing at -2. But look at what happens. Something special happens here between -2 and -1. Your graph goes from below the x-axis to above the x-axis. So obviously, if you're going to go below to above, you have to cross the x-axis. Therefore, you have to have an x-intercept. And since this problem says that we want to locate each of the real roots, we want to locate those x-intercepts between the consecutive integers. So there's an x-intercept between we're going to put it like this. Sorry, I need to list this off from -2. I don't know why I wrote 0, but from where we first saw it, so going from negative to positive. So between -2 and -1. And then we're going from positive to positive, so we're above and above, nothing's happened. But here I'm going to go from above to below, so between, let's see, 0 and 1. So on that interval. And then from below to above, so from 1 and 2. So we have x-intercepts between -2 and -1, 0 to 1, and 1 to 2. So if we want to list that in interval notation, you can, but this is the exact same thing. If you want to refer to it like this, I'm totally okay with that. It's just knowing that if you cross from positive to negative, from above to below, you get an x-intercept. From negative to positive, so from below to above, you have to have another x-intercept. It's as simple as that, and that's the intermediate value theorem. Okay, let's call this lesson finished, and we're going to go on to the next one.